Hello again, this is Bruce Wallenberg. This is Lecture 5 on linear programming. This is a very, very useful, if not in many ways the most useful optimization technique ever devised, used extensively in many, many different fields, and used extensively in our text. Here is our problem. I set this problem up so that you could see it in terms of two power plants. And I said the variables, we like to use x's in LP. So x1 is the output of plant 1 and x2 is the output of plant 2. And we said the benefit of using plant 1 is this cost, or this benefit in dollars per megawatt hour, and the benefit here is 3 and is 5. So the objective function then is simply to maximize this 3 times x1 plus 5x2. Now note, this is a linear function. This is the first thing that you run into with LP, is that the objective function is a linear function. There's no squares or any other functions in there that other than just constant coefficients times the variables. I'm going to later on switch over to a minimization in order to do this, because LP is always minimizing, and it's very easy to minimize a function that if you've already got the function like this, and you just minimize the negative of the function which maximizes it. So we'll see that later, but right now we're talking about maximizing. We say the maximum production for plant 1 is 4. The maximum production for plant 2 is 6. So these are inequality constraints. Basically this says, and we'll see it, that x1 is less than or equal to 4, x2 is less than or equal to 6. But we put these in terms of b. These variables b are what we call the right-hand side. In addition, we're going to add this constraint that must be met, that 3x1 plus 2x2 must be less than 18. Now, the basic mathematical statement of the problem then is maximize this. Here is my first inequality constraint. x1 is less than or equal to 4. x2 is less than or equal to 6. And then I have this combined 3x1 plus 2x2 constraint, and I want the x1 and x2 to be positive numbers, so they're greater than 0. I could have some equality constraints. These are all inequality. I could have equality constraints in the problem as well, but it turns out that this one does not, and it doesn't take anything away from it. Now here is a picture. Here we have x1 on the horizontal, x2 on the vertical, and it turns out that the x1 line down here, this is the constraint, x2 greater than 0. That means that all the values have to be up here, and I can't have anything down here. So I'll draw some lines, some crosshatch down here. It means you can't put any variables down there. Similarly, this line here, which I'm trying to follow the best I can with the mouse, this is the x1 has to be greater than 0. That means that I can't have anything out here. Okay, so this is all crosshatched. Now I come over here and I say, well, if x1 is less than or equal to 4, it means that this line is as far as you can go with x1. So out here is all crosshatched. Up here, x2 less than 6 is this line here. And again, I have all the crosshatching up here. And last of all, I have this constraint, 3x1 plus 2x2 less than or equal to 18. So you can see that the feasible region is the one that's in the light blue color on this diagram, is inside here. And these points where the constraints cross each other, we put a big dot. Okay, and the dots have a significance later on. So this is what we call the feasible region. Any number that's in this region or on the boundary, very important, it's got to be in the region or on the boundary, is considered feasible, meaning it satisfies all the constraints. So here's a summary. We say we're going to minimize this. Now, notice that I've now switched to minimize. The LP always works. All the logic is based on minimization, and so if you have a problem that wants to maximize, just take the negative. You'll see this later on in the course where we're doing a function that's got generation cost and worth of load supplied, and we minimize it instead of maximize it, so we just negate it. Here's my constraint. There's a matrix. There's the variable x. That's a vector. The matrix is less than or equal to b. So then this is a matrix. We could have drawn it like this. The matrix A less than or equal to b. That's the form that you put the constraints in. And then we always say that the x's are greater than 0. And the x's are part of the right-hand side, the real numbers. So x is a vector, n minus 1. C is a vector of cost coefficients. A is an m by n matrix of constraint coefficients. So there's m constraints and n variables. B is the right-hand side, which is m by 1. Now, last of all, we go back to this picture here, just like we had before, but see these lines here are the contours. They are the contours. And the objective function, now the objective function in our case is to maximize that function. And this is the optimal solution. We can tell you that right away. That function right here, 2, 6, the function 2 times 3 plus 6 times, I'm sorry, let's go back. There's our objective function. So if this was 2 times 3 would be 6. 5 times 6 is 30, so it would be 36. And that's the maximum right there. So that's the maximum. Again, we're minimizing the negative of it, and it'll get to the same point. Now, so this is where we want to get to. We're going to start things off down here, as you're going to see in a minute. We're going to always start at the origin. So what we do is we put this in what the mathematicians like to call canonical form, and what we're doing is we're adding more variables. These variables over here are called slack variables, and essentially this allows us, these are the original variables, as you can see, x1 and x2, but the slack variables allow us to start with x1 equal to 0, x1 equals 0, and x2 equals 0. So if they're equal to 0, then x3 is equal to 4, x4 is equal to 6, and x5 is equal to 18. We don't do anything with the cost function now. So as I said, we said we were going to start with x1 and x2 equal to 0, and so we add these other variables to the problem. Notice that what that did for the A matrix is it changed all of the inequalities to equalities. These are all equalities now. We've changed them to equalities by saying x1 is less than or equal to 4, but x1 plus x3. x3, you can say it takes up the slack. If that helps you, it takes up the difference between whatever x1 is and the constant on the right hand side, 4 over here. But this gives us a way to start out. We set the values of the slack variables, and then we can start the problem. So everything starts off that way. So we say that we partition the set into basic and non-basic variables, and the basic has the b, and the non-basic here we call n. So A is partitioned into b and n, and x is partitioned into partly b and partly n, and so is the cost. There's cost coefficients that are basic and non-basic, and you can see them down here. This is in your appendix of that on LP. B is the non-singular square n by n submatrix called the basis. So this is square. N is the matrix containing the remainder of the columns of A. XB is the vector of basic variables that are in what we call the basis. XN is a vector of non-basic variables. CB, of course, that's the cost coefficients on the basic and the non-basic. Now, let me go back here. When we started out, the basic variables were the slack variables. So this is the B set over here. This is the N set over there. Okay. Basic and basic feasible solutions. If you set up a set of variables x that merely solves this equation, that is a solution. If it solves that set and the variables are all greater than 0, that's a feasible solution. If it's a solution and it's feasible and all of the x in the non-basic are 0, we've now got what we call a basic feasible solution. What you're going to see is that we move from solution to solution, and it just simply means we're moving from one dot to the next dot on that diagram. All basic feasible solutions, I'm not going to try to go through every single one of these. Here's the initial. Here's the initial where we had the non-basic and we had the basic here, and this is the original A over here, and this is the right hand side, and then we started to say, well, let's say that I have a solution with x1, x2, and x3. And then they would come up with these values, and z would equal this. It turns out that is the optimal solution. That is the optimal solution. But if I just kept going, I said, well, I suppose I had x1, x2, and x4. Well, then I get minus 27. That's not as negative. And the other sets that I could use, these other three sets, I'll let you look at those in the appendix, all fail on some condition. You notice we get some non-positive values here. Here we get a bunch of infinity. There's no solution to these values. So the A is a singular matrix in that case. You can't invert it. Last of all, we get this case down here, x1, 4, and 5. You get a z of minus 12. Still more. We can just keep going. We're going through all possible combinations of 3 in here. This fails on a condition. This is a good condition, but it's not an optimum. This is no good. We've got a singular matrix. Here's where we are at the beginning. This is where x1 and x2 are 0. And so we're only saying that the basic feasible, so at the very beginning is the slack variables. So the simplex method, starting with our basic LP, you minimize the cost, keeping the constraints and keeping these variables greater than 0. You partition the matrix into basic and non-basic. So you've partitioned things down here, for example. We've already shown that we've done that. But now we're going to make some multiplies, and so we're going to take this variable, this b, and we're going to multiply it times the n and times this b, and we're going to flip this to the other side so that we can get an expression for xb. So that's the first thing we do. xb is b inverse times the right hand side minus b inverse n times xn. And then I'm going to take the expression for this and I'm going to put it back up into the expression for the cost here, and I get this expression over here. So we like to say that this b inverse b is b tilde, lambda transpose is cb times b inverse, that's this thing in here. And last of all, I'm going to call b inverse n the matrix Y. Lambda is called the dual variables or the dual variable vector. So we have a setup that looks like this now. Now I have the xb, these are the basic variables. This is a constant minus y times x. Now these are the non-basic variables. And the whole idea now is to take variables out of the basis and to take a non-variable and put it into the basis. And we're going to show how we do that. If we define D transpose as this, as a reduced cost vector here, and allow us to write a new standard form like that. And we're going to do something called pivoting, and you'll see that we're going to pivot on row I and column J right in here, and that's in this Y form. Now notice this is xb equals b tilde times y times xn. That's this equation right here that we're going to pivot on. So this is I'll just put pivot. So we're going to pivot on that. Here's the rules. I'm going to go through it here, but you need to sit down and think about it for a while and try it out a little bit to get a good understanding. If d sub j is positive, the objective function decreases if a non-basic variable increases. Okay. If the non-basic variable increases, the basic variable xbi. Now this is we've got a column I that selects one of the basic variables. Decreases if this is positive. If some yij's are positive, the corresponding variables x, bi decrease if the non-basic variable x increases. The non-basic variable x can be increased until the first basic variable goes to 0. That's the important thing. I want to take a non-basic variable and make it basic, and I want the corresponding basic variable to go to 0, meaning it leaves the basis and becomes non-basic. So I'm exchanging them, so to speak. That is until this becomes 0 for the first I. And what you do is you just have to find that, and we'll show you that in a second. So the value becomes the minimum over all of those variables of this. And the value of the basic variable becomes 0. So this is the value that the non-basic variable, but we want to take the minimum of these numbers here. They're positive. Here's the strategy or pseudocode. You get a basic feasible solution. Well, that's usually done by setting up so that the original variables are all equal to 0 and the slack variables are now the basis. Find out if the current solution is a minimizer or is the minimum. If all dj are 0, stop. The current solution is the minimizer. Else, find out which non-basic variables enters. It must be positive dj. Find out which basic variable leaves. That's the minimum over these numbers here. And now you do this pivoting operation where you eliminate items in y, and you exchange the basic and non-basic variables. Get a new basic feasible solution, and then go back to step 2. And you keep doing that until this condition here. So when we do that, what happens is we start out down here at our initial basic feasible solution, and the first thing that happens is that it goes to this point. Okay, that's the first jump. Now this is the value of the objective, minus 12. The next thing that happens is we go to this point where the objective is minus 27, and then we go to this point, minus 36. And LP always runs itself. I drew these as big arcs, but it's better to think of it as always running along the constraint. So it runs this one first, then it comes up, so it's always making its way along the edges, and then it comes up here to the edge. This is always true of LP until you get to the top here, and that's the minimum down here. So that's the solution. So it finds the solution, and the process that we're using here to go from this to this to this to this is that pivoting. So you pivot once, then you pivot again, then you pivot again, and you get to the minimum solution. Some other features that I strongly recommend: upper and lower bounding simply says that any variable can have an upper and lower bound. And I love the LP that's in the MATLAB optimization toolbox. It's based on a code called linprog, extremely powerful. It can do sensitivity. The MATLAB LP allows students to see the lambda values so that we know how much things are going to change if we change variables. Those lambdas are extremely valuable as well. You can even in the MATLAB you can force an initial solution if you know that you can start out quicker that way. You don't have to. So those are just some useful features that are in the MATLAB LP. There's lots of LP codes out there, but for students, I recommend the MATLAB code. Thank you very much.